At this very moment, 2 human-built machines are drifting through interstellar space. Not 1, 2. Nearly everyone has heard of Voyager 1, the most distant object humanity has ever launched, the craft that broke through into interstellar space back in 2012, and has been beaming data home from beyond our solar system's edge ever since. It's the one carrying the golden record, the one that dominates the headlines, the one everybody references. But there's a second probe out there too. Quieter, less famous. Traveling through the void 13 billion miles from home on an entirely separate trajectory, sampling an entirely different slice of interstellar space, and carrying a piece of hardware that Voyager 1 lost long before it ever reached the Heliopause, hardware that would turn out to be the single most vital tool for making sense of what actually exists at the solar system's outer edge. Its name is Voyager 2, and what it detected the moment it crossed into interstellar space, what its rare, irreplaceable instrument recorded as it pushed through a boundary no theoretical model had ever gotten right, didn't simply back up what Voyager 1 had already found. It clashed with it. It muddied it. It opened up questions Voyager 1, despite all its remarkable accomplishments, was never equipped to answer, because Voyager 1 was flying blind to the one thing that mattered most at the Heliopause, and Voyager 2 was not. And right now, in the summer of 2026, Voyager 2 is on the verge of becoming the single most consequential spacecraft in this mission's entire history. Not because of a new discovery, but because of what NASA is preparing to do to it. A maneuver so dangerous, so untested, so absolutely all or nothing that the engineers working on it gave it a nickname, the Big Bang. A single, synchronized overhaul of every remaining power system on the spacecraft, carried out across a communication gap of more than 16 hours in each direction, with zero fallback and zero chance for a do-over if anything goes sideways. If this works, Voyager 2 buys itself more time, and everything NASA plans to attempt on Voyager 1 in July hinges entirely on whether Voyager 2 makes it through first. Stick around, because this is a story almost nobody's telling, and it matters more right now than anything else happening in the Voyager program. Voyager 2 lifted off on August 20th, 1977, 16 days ahead of Voyager 1. That numbering isn't a typo or a mix-up. It reflects the order the 2 probes were expected to arrive at their destinations. Voyager 1 rode a quicker path, one built to swing past Jupiter and Saturn before angling out of the solar system altogether. Voyager 2 was handed a longer, more intricate route, one built to accomplish something Voyager 1 never could. Something that, at the time of launch, no spacecraft in history had ever pulled off. And something that, nearly 50 years on, no spacecraft has managed to repeat since. Voyager 2 remains the only spacecraft ever to visit all 4 outer planets. All 4. Jupiter, Saturn, Uranus, and Neptune, every gas giant and ice giant in our solar system, examined up close with instruments purpose-built to read their atmospheres, their magnetic fields, and their moons. Voyager 1, by contrast, swung past Jupiter and Saturn and then climbed north, out of the ecliptic plane, giving up any shot at Uranus or Neptune in exchange for a tighter flyby of Saturn's moon Titan and a shorter road to interstellar space. That trade-off was deliberate. 2 spacecraft, 2 missions, 2 very different answers to the question of what really lies at the solar system's far edge. The cost Voyager 2 paid for touring all 4 planets was time. Its path, bent and boosted by gravity, assists from each planet along the way. Simply took longer to get there. Voyager 1 broke through the Heliopause in August of 2012. Voyager 2 didn't cross it until November 5th, 2018, 6 years and 3 months afterward. For all that time, Voyager 1 had already been sitting in interstellar space, already logging plasma readings and magnetic field data from beyond the boundary, already sending back numbers that were baffling researchers and forcing a rethink of existing models. For 6 full years, Voyager 1's data hinted that something remarkable was unfolding at the Heliopause. But the picture was missing pieces, because the one instrument that could have filled them in had already died back in 1980. Here's a detail almost nobody brings up when discussing what Voyager 1 found at the Heliopause. Its plasma science instrument, the device built to directly clock the temperature, density, and flow speed of plasma, both inside the heliosphere and out in the interstellar medium, went dead in 1980, not at the Heliopause, not in interstellar space, before the spacecraft had even reached Jupiter's orbit on its way out of the solar system, 4 decades before it ever crossed the Heliopause, before any of its interstellar discoveries happened. The one tool best suited to explaining what that boundary actually looks like from the inside had already gone silent. That meant when Voyager 1 finally crossed the Heliopause in 2012, it had no way to directly measure the plasma on either side of the line. Scientists could piece together an approximation using other instruments, the cosmic ray detector, the magnetometer, the plasma wave subsystem. But direct measurement simply wasn't possible. They were working around a hole in the data, a hole that had already existed for 32 years by the time the crossing finally happened, and one they had no way to patch. Voyager 2's plasma instrument, on the other hand, was still alive. When it crossed the Heliopause on November 5, 2018, it carried a working plasma sensor, a piece of equipment Voyager 1 had lost before the Cold War even ended. And at that boundary, that instrument produced a data set researchers would go on to call historic, the first direct measurement ever taken of plasma on both sides of the heliopause, inside the heliosphere and out in interstellar space, captured simultaneously as the spacecraft made the actual crossing for the first time in human history. 5 separate papers, published together in Nature Astronomy in November 2019, laid out what Voyager 2's instruments had found at the heliopause. And the findings upended assumptions in ways that genuinely stunned a field that had spent 6 years working off Voyager 1's incomplete picture. The first shock was how thick the boundary turned out to be. Researchers had assumed the heliopause would be a fairly narrow, sharp-edged transition, a clean line where the solar wind stopped and interstellar space began. Models pictured it as a slim zone, maybe a few 100,000 kilometers across, where the hot, fast-moving solar wind met the cold, dense interstellar plasma, and the two briefly blended before pulling apart. What Voyager 2 actually found was a much wider layer, a distinct transition zone roughly 100 million miles across, sitting just beyond the heliopause, not on the solar wind side, but out in what was supposed to be pure interstellar territory. Instead of interstellar plasma beginning immediately, Voyager 2 picked up a region where interstellar particles had pushed inward through the boundary like roots, forcing their way through rock, tendrils of interstellar material reaching more than 100 million miles inward, mixing with the solar environment in ways no model had predicted. Voyager 1 had spotted something similar on its own approach, but not identical. Before crossing, it passed through a zone where the outbound solar wind had slowed nearly to a standstill, a stagnant pocket just inside the boundary where the wind had essentially run out of push before it could travel any further. Voyager 2, coming in from a different direction and crossing at a different point on the heliopause, encountered something else on its approach. A thin layer nearly the same width as Voyager 1's stagnant zone, but with entirely different plasma properties. 2 spacecraft, 2 crossings, 6 years apart, different regions of the same boundary, and 2 completely different structures. Stamatios Krimigis, principal investigator on the low-energy charged particle instrument at the Johns Hopkins Applied Physics Laboratory, summed up what this meant with a clarity that captured the scientific community's reaction perfectly. The fact that both probes hit the heliopause at almost exactly the same distance from the Sun, 121.6 astronomical units for Voyager 1, 119 astronomical units for Voyager 2, was in itself deeply strange. One crossing occurred near solar maximum, when the Sun's output was running high. The other happened near solar minimum, when activity was low. Theory predicted the heliosphere should swell during active periods and shrink during quiet ones. Instead, both probes hit the boundary at essentially the same distance. "We don't understand why that is," Krimigis said plainly. "We do not understand why." Coming from one of the mission's senior scientists, someone with decades of Voyager data behind him, that's not a small admission. It's a flat statement that something basic about how solar activity relates to the size of the heliosphere doesn't behave the way the models claim it should. The second major surprise from Voyager 2's crossing had to do with temperature. Plasma inside the heliosphere, driven outward by the solar wind, runs hot. Not hot in any everyday sense, but hot in the plasma physics sense, meaning its particles are moving extremely fast. Scientists expected that as this hot plasma reached the heliopause and met the colder, denser interstellar medium pressing in from beyond, the resulting temperature shift would define the crossing. What Voyager 2's plasma instrument actually measured was a temperature drop at the heliopause that was far sharper than any model anticipated. The plasma dropped from the heat of the solar wind environment to the much colder interstellar medium across a far narrower zone than expected. What made this even more striking was the density on the inside. Solar wind plasma is relatively thin. Beyond the heliopause, out in interstellar space, it's considerably denser. Both Voyager 1 and Voyager 2 confirmed this, and together, the 2 data points gave scientists their first ever stereo measurement of interstellar plasma density. The space between stars isn't empty. It's filled with plasma more than 40 times denser than the solar wind found near the heliopause. But there was more buried in Voyager 2's plasma readings that reshaped a critical piece of the picture. The temperature of the interstellar plasma, measured directly for the very first time thanks to Voyager 2's working instrument, came out at 30,000 to 50,000 degrees Kelvin. Hot by ordinary standards, yes, but far cooler than the plasma sitting just inside the heliopause boundary, which the spacecraft clocked at tens of millions of degrees. The boundary was real. The temperature gap was real. And this direct reading, something Voyager 1, without a working plasma instrument, simply could never provide, handed scientists a hard number where, before, they'd only had a theoretical guess. That earlier guess turned out to be off by a factor of 2. The third surprise, and the one Ed Stone, the Voyager project scientist at Caltech, a post he'd held since before either spacecraft launched, called the most remarkable of all, concerned the heliopause itself. It leaks, not in a figurative sense, literally. The boundary between the solar wind and interstellar space is not a sealed wall. Particles cross it in both directions. On its approach, Voyager 1 had picked up what looked like tendrils of interstellar particles pushing inward through the boundary, slipping into the heliosphere from outside. Voyager 2, approaching from the south, saw the opposite. A trickle of low-energy particles escaping outward through the heliopause into interstellar space, detected before the spacecraft had even made the crossing. That leakage showed up at two separate entry points, at different stages of the solar cycle and different regions of the boundary, meaning whatever was driving it wasn't some local fluke. It was a fundamental property of the heliopause itself, something no pre-Voyager model had accounted for. Two spacecraft, approaching from opposite directions, 6 years apart, both discovering the same leaky border. Different mechanisms at work on each side, interstellar particles pushing in on one end, solar particles slipping out on the other, but pointing to the same underlying truth. The heliopause is a boundary that material crosses constantly in both directions. It behaves less like a wall and more like a coastline, with surf breaking both ways at the meeting point of two oceans. The Voyager probes are showing us how our sun interacts with the stuff that fills most of the space between stars in the Milky Way galaxy, Stone said when the 5 Nature Astronomy papers were announced. The wording there is deliberate, not how the sun's influence ends and interstellar space takes over, how the sun interacts with interstellar space. Not a tidy dividing line, but an ongoing, tangled, active relationship between two environments that refuse to stay cleanly on their respective sides. And both spacecraft, even now, are still moving through a disturbed transitional region, not yet in undisturbed interstellar space. Even at 13 and 16 billion miles from the sun, both Voyager probes are sampling territory still shaped by the solar system they left behind. Now step back from the science for a second and consider what Voyager 2 actually means within the full sweep of the Voyager mission, because the discoveries are only half the story. When Voyager 2 was assigned its route, the one that carried it past all 4 outer planets before it ever aimed for interstellar space, mission planners already knew it would get there later, knew it would cross the heliopause from a different angle than Voyager 1, and knew the two craft would end up giving two very different views of the same boundary. None of that was an accident. The Voyager team, working in the 1970s with computing power weaker than a modern pocket calculator, deliberately built a 2-spacecraft mission specifically so they wouldn't be stuck relying on a single data point. One spacecraft alone can't tell you whether what it finds is normal or an outlier. 2 spacecraft, approaching from different angles at different times, can start to sketch out the real shape of the boundary. What the planners couldn't have fully foreseen was that the instrument that would end up mattering most for understanding the heliopause crossing, the plasma science instrument, would fail on one spacecraft and keep working on the other. That Voyager 2's plasma detector, still functioning after more than 4 decades exposed to the radiation environment of the outer solar system, would end up supplying data Voyager 1 simply couldn't, closing a gap in the record that had existed since 1980. The division of labor between the two probes was planned. How that division actually played out was not. That's the essence of what Voyager 2 represents. A design contribution that ended up exceeding its own blueprint in ways nobody could have predicted. A mission engineered to last 4 years, meant to wrap up in 1981, still transmitting in 2026 from a region of space no instrument had ever sampled directly before, with hardware that has outlasted every projection ever made about its working life. Right now, in the summer of 2026, the JPL engineering team's attention is fixed on Voyager 2 like never before. It currently runs 3 functioning science instruments, the plasma science instrument that made the heliopause measurements possible among them, alongside a working magnetometer and a working plasma wave subsystem. Together, those 3 instruments are delivering something no other tool in the history of astronomy ever has: a continuous, real-time, in-situ record of conditions in the interstellar medium, gathered by a spacecraft physically sitting inside that medium, moving through it at 34,000 miles per hour. But the power supply keeps shrinking. The same slow, mathematically inevitable decay of plutonium-238 that's steadily eating into Voyager 1's capabilities, stripping away roughly 4 watts of available power every single year, is doing the exact same thing to Voyager 2. At launch, each spacecraft carried roughly 470 watts, generated by 3 onboard radioisotope thermoelectric generators. Today, Voyager 2 has a slight power edge over Voyager 1, which is why it's still running 3 instruments, while Voyager 1 dropped to 2 after its LECP instrument was shut down in April 2026. But that cushion isn't large, and it keeps shrinking by 4 watts a year. The Big Bang is meant to buy back some of that margin. As NASA's Jet Propulsion Laboratory describes it, the procedure means swapping out a whole cluster of powered components in one shot, switching some off entirely, replacing others with lower power substitutes, all to keep the spacecraft warm enough to keep collecting science data. The nickname comes from the all-at-once nature of the plan. Not a gradual, one change at a time rollout, tested and confirmed before moving to the next step. Everything at once. A total rewiring of how power moves through every surviving active system, executed in a single coordinated operation across a communication link where each command needs more than 16 hours just to arrive, and each response needs more than 16 hours to come back. The reason for doing it all in one shot instead of step by step comes down to the danger of the in-between states. During any reconfiguration of a spacecraft's power systems, there are transitional moments where the system belongs to neither the old setup nor the new one. Those in-between moments can trip fault protection systems, automated safety routines built into both spacecraft that will start shutting components down on their own the instant they detect power draw exceeding what the generators can deliver. The entire logic behind the Big Bang is to spend as little time as possible in those risky transitional states by making every change at once and racing through the switch as fast as it can be done. If it works, if the new power layout trims enough waste across the system to claw back real headroom in the power budget, it could add at least a year, possibly more, to the working life of Voyager 2's science instruments. And if the Big Bang succeeds on Voyager 2, the same procedures slated to be attempted on Voyager 1 no earlier than July 2026, with hopes that success there might even allow engineers to bring the LECP instrument, shut down back in April, back online. Voyager 2 goes first, not because it matters less, but because it's slightly closer to Earth, carries a bit more power, and is therefore the safer candidate for testing a procedure that's never been tried before. What's actually riding on keeping Voyager 2's instruments alive doesn't have a simple answer. It's really several questions, stacked on top of each other, each one pointing at a gap in human understanding that only these two spacecraft are currently positioned to close. The structure of the heliosphere is one of them. The 5 Nature Astronomy papers from 2019 established that the Heliopause leaks, that it sits at roughly the same distance from the Sun, no matter the level of solar activity, that the interstellar plasma beyond it is denser and colder than expected, and that the boundary looks structurally different depending on which direction you approach it from and which instruments you're carrying. But those findings raised at least as many questions as they settled. Why does the heliopause sit at the same distance during both solar maximum and solar minimum? If it isn't the strength of the solar wind, what determines where the boundary actually sits? What's driving the two-way particle leakage? And how does that leakage shift as the Sun travels through different pockets of the galaxy's interstellar medium? The overall shape of the heliosphere is still genuinely unresolved. Some models predict a long comet-like tail stretching out behind the Sun, opposite the direction of its motion through the galaxy. Others argue for something closer to spherical, or even lemon-shaped. Voyager 1 and Voyager 2 are each sampling a single point along the heliosphere's outer edge, one roughly toward the nose, one toward the flank, and their combined readings are among the primary tools scientists have for testing these competing theories. The longer both spacecraft stay alive, the more data piles up, and the tighter those models can be constrained. The interstellar magnetic field is another open question. Both probes have measured the magnetic field out in interstellar space beyond the heliopause, and the orientation of that field carries implications for how the entire heliosphere sits relative to the galaxy's broader magnetic structure. Voyager 2's magnetometer, still operating in 2026, keeps contributing readings that help map the local interstellar magnetic field in the southern half of the heliosphere, a region distinct from the northern territory Voyager 1 is sampling. And underneath every one of these specific scientific questions sits a larger, harder one. What happens once both spacecraft finally fall silent? There's no replacement waiting in the wings, no follow-up mission currently bound for interstellar space, no instrument anywhere within 50 billion miles of where these two probes sit right now. And there won't be for decades. Once the last of their instruments goes dark, the map they've been drawing of the interstellar medium simply stops being updated. Every question they raised but never fully resolved will sit there unanswered until some future mission, not yet funded, not yet designed, not yet approved, eventually retraces their path and reaches the same boundary. Laid out plainly, Voyager 2's accomplishments are almost too many to take in at once. It's the only spacecraft ever to visit Uranus. During its January 1986 flyby, it uncovered 10 previously unknown moons and 2 new rings circling the planet. It measured Uranus's extreme 97.77 degree axial tilt and its ice giant interior composition, and found a magnetic field so far off-center from the planet's rotation axis that it still challenges every model of how planetary magnetic fields form. It's the only spacecraft ever to visit Neptune. During its August 1989 flyby, the final planetary encounter of the entire Voyager program, it discovered 6 new moons, including Proteus, a moon large enough that it probably should have been spotted from Earth long before Voyager arrived. It clocked Neptune's supersonic winds at 2,400 kilometers per hour, the fastest wind speeds ever measured in the solar system at that time, And it took detailed observations of Triton, Neptune's largest moon, spotting active nitrogen geysers blasting material 8 kilometers into its thin atmosphere and determining that Triton was almost certainly a captured Kuiper Belt object, a world born elsewhere in the solar system that was pulled into orbit around Neptune by gravity, its surface reshaped by the tidal heating produced as its orbit has slowly circularized ever since. It found a 14th moon at Jupiter during its 1979 flyby. It delivered data on Saturn's rings that revealed a level of structural complexity Earth-based telescopes had never been able to detect. It confirmed the active volcanic eruptions on Io that Voyager 1 had first spotted, catching the volcano Prometheus mid-eruption, throwing a 200-kilometer-high plume of sulfur dioxide frost into space. And it captured the images of Europa's icy crust, the fracture lines, the surprising lack of large craters, the reddish-brown staining running through the cracks between ice blocks that first hinted at a liquid water ocean hidden beneath the surface. Those images fueled decades of scientific interest in Europa as a possible habitat for life and eventually helped lead to the Europa Clipper mission now underway. All of that from a spacecraft that launched on August 20th, 1977, 49 years ago. Built using technology from before the internet, before personal computers, before GPS, before cell phones existed. Designed to last 4 years, still transmitting, still gathering data, still delivering, because of the unusual route it was handed and the instrument that survived when Voyager 1's counterpart didn't, something no other spacecraft in history has ever offered. Direct measurements taken from inside interstellar space from a different direction than Voyager 1, with a functioning plasma instrument for the first time ever. The Big Bang tests are underway right now. Across May and June of 2026, the JPL engineering team has been working through the procedure on Voyager 2, checking whether the simultaneous power reconfiguration can run cleanly, whether the fault protection systems stay quiet through the transition, and whether the new power layout actually delivers the efficiency gains the calculations predict. Every command sent during these tests takes more than 16 hours to reach the spacecraft. Every reply takes more than 16 hours to come back. A single diagnostic step eats up more than a full day of communication time on its own. The team carrying out this work is small. It has always been small. The original Voyager engineers have mostly retired, and their replacements had to teach themselves programming languages and spacecraft design conventions from an era that predates their own careers, just to be able to talk to these machines the way the machines were originally built to be talked to. The knowledge needed to keep Voyager 1 and Voyager 2 running in 2026 doesn't show up in any modern aerospace engineering curriculum. It's living, institutional knowledge, held by a specific small group of people at a specific building at JPL, the kind of knowledge that can't simply be reconstructed from documentation once the last person carrying it retires. They're still there, still working, still sending commands across 13 billion miles of empty space and waiting 16 hours for the reply to arrive. Still weighing the trade-offs between instrument capability and spacecraft survival that determine exactly what this mission can deliver in any given week. Still, as of the summer of 2026, keeping 2 spacecraft alive and transmitting from interstellar space, with a procedure nicknamed the Big Bang standing as their best remaining tool for buying more time. What Voyager 2 found at the Heliopause, what its plasma instrument measured firsthand, what those 5 Nature Astronomy papers documented, what the leaky boundary and the unexpected density and the temperature readings and the magnetic field data all add up to, paints a picture of a solar system that isn't sealed off from the galaxy surrounding it. That's what 49 years of continuous operation, and 1 plasma instrument that happened to survive, ultimately delivered. Not a confirmation of what scientists expected, but a string of surprises still being unpacked, explained, and folded into new models. Models that will eventually be tested by future spacecraft, if and when those spacecraft ever get built, funded, launched, and delivered to the same boundary. Until then, 2 machines roughly the size of small cars, powered by the slow decay of plutonium sealed into their generators nearly 50 years ago, are still out there in the darkness between the stars. Still transmitting, still measuring, still mapping a region of the universe no human-made instrument had ever sampled directly before they arrived. Voyager 1 is the one everybody knows. Voyager 2 is the one that filled in what Voyager 1 physically could not measure. The twin that toured every giant planet in the solar system, the one that crossed the Heliopause with a working plasma instrument and told us, for the first time in human history, what the temperature and density of interstellar plasma actually look like when you measure them directly instead of guessing at them through theory. The signal from Voyager 2 takes more than 16 hours to reach Earth. It arrives faint, stretched thin by distance, carrying information from a place that remains genuinely out of reach by any other means we currently have. And right now, in the summer of 2026, NASA is attempting something on this spacecraft that has never been tried before at this distance, a procedure they're calling the Big Bang, a single, all-at-once overhaul of everything. One shot, No second chance. And the outcome will decide not just what happens next for Voyager 2, but what becomes possible for Voyager 1 come July. The signal is still crossing 13 billion miles, still traveling through 16 hours of transit time at the speed of light, still completing a communication loop that takes more than a full day round trip, and it's still coming. If you want to know the outcome of the Big Bang tests on Voyager 2, the instant NASA confirms it. If you want to understand what it means for Voyager 1, for the future of the LECP instrument, for the last real-time data stream humanity will get from interstellar space for at least the next quarter century. Subscribe now and turn on notifications. This channel covers the real science, the verified data, the actual findings from the actual spacecraft, given the weight they deserve, without inventing a single thing the instruments never measured. What Voyager 2 discovered at the Heliopause stands as one of the most significant data sets in the history of planetary science, and almost none of it got the attention it deserved when it was published back in 2019. We're fixing that, one video at a time. Subscribe. Hit the bell. The Big Bang results are coming. The November 18th, one light day milestone for Voyager 1 is coming. The July attempt on Voyager 1 itself is coming. When those results land, you'll want to already understand exactly what you're watching. The signal is still coming.